Okay, folks, let's talk about the next high energy molecules containing a thioester bond, most commonly seen in the CoA molecule. And on the screen here, I've shown you one version of this molecule in acetyl-CoA. So CoA is used largely as an acetyl or an acyl carrier. For example, you'll see it quite frequently in lipid synthesis, for example, where we kind of need to add carbon units together to form lipids. Now, the high energy bond that we're talking about is the thioester bond, or the bond between this sulfur and carbon. This is the bond connecting CoA to the acetyl group. So everything else that you see here, folks, right, is coenzyme A or CoA. So I want you to recognize it as a very large organic molecule. Of course, we should recognize the nitrogenous base, the sugar ring, a few phosphates there, and then a large organic section here leading up to the thioester bond with an acetyl group. And we know these bonds are high energy, and actually they're slightly more exergonic than synthesis of a phosphoanhydride bond as seen in ATP. And this is because the orbital overlap between that sulfur and carbon is not ideal. And I'll show that to you on the next slide, okay? And so we can imagine that cleavage of this bond releases a lot of energy, and oftentimes when we see that happen in biochemistry, it results in synthesis of other high energy molecules, such as we will see in the TCA, synthesis of GTP, which is similar to ATP. Now let's try to visualize this for ourselves, okay? And I'll try to compare this thioester bond to your regular ester containing oxygen. So in the ester bond, we're looking at the bond between, right, oxygen and carbon. And the overlap here of the orbitals is ideal, right? We have kind of this oxygen, and this is a cartoon, so please excuse me. This oxygen overlapping perfectly with the carbon. Now, what this orbital overlap allows in an ester bond is for this like beautiful resonance stability that you've seen in your classes such as organic chemistry. And we know resonance increases stability of bonds, so the ester bond is very stable. That is not true for a thioester bond. So we'll just redraw this here. And what's happening is that the orbital overlap between sulfur and carbon is a little bit off. And so I'm going to have a hard time drawing this for y'all. But right now, the orbital alignment is not the same as with oxygen. Maybe they're a little bit misaligned, or the atomic radii of the atoms is not quite right for that great overlap of the electron clouds. And so what happens is this molecule is less resonance stabilized. And you should understand that things that are less stable are higher energy. So when we cleave this bond here between the sulfur and the carbon, a lot of energy is released. And that's why bioester bonds are considered high energy bonds.